Let's now look at some reactions involving 1,3-dicarbonyl compounds. Specifically, we're going to talk about what's called the acetoacetic ester synthesis, or AAE. And what that allows us to do is start off with this compound, which is acetoacetic ester, and we end up with a methyl ketone. And you can see that we can vary these R groups here, which allows us some great versatility to be able to pretty much create any methyl ketone that we want to create. The other one I'd like to look at is called the Malonic Ester synthesis, which is pretty similar to the AAE synthesis, except that instead of a methyl group here, we have a methyl ester group. And the malonic ester, when all is said and done, produces a carboxylic acid as a product. And again, we can get the same kind of versatility by adding pretty much any R groups we want to this carbon, so we can end up with any carboxylic acid we might desire. Alright, so let me take you through an AAE synthesis step by step, and I'll show you the process as we go. So here is an example of an acetoacetic ester synthesis. You can see we end up with a methyl ketone as a product. In the first step, what we're using is the acetoacetic ester, and here we've got a base, and it's sodium methoxide, NaOMe, in methanol. So the active ingredient here is OMe minus, and that will take a proton off the carbon that lies in between the two carbonyl groups, which leaves us with this anion right here. Okay, the reason we get this anion and not the hydrogen off this one to leave this anion is that this anion is actually resonance stabilized because it's between these two carbonyl groups. So the negative charge is right next to this C double bond O and right next to this C double bond O. So it can resonate with this one and it can resonate with this one. If we put it over here, the negative charge could only resonate here. So we know that the negative charge will form on the carbon between the two carbonyl groups. Then we can throw in the alkyl halide, and that will produce this compound that is now substituted off the middle carbon. Alright, so that explains how we get this first product here. Let me move that Br negative. It's not really meant to be so close to that. I'll put it over there. There we go. So we get this product, and you can see that if we repeat the process, we can put another alkyl group on, and that's what we're going to do in the second step here. And still, we're going to end up removing that middle proton. We still have one proton left, and that's right here. And that will be pretty much as acidic as the first proton was. So the OMe minus comes in, removes the proton, and we're left with this anion. And this anion can then attack this alkyl bromide. Notice that it always attacks the C to which the bromine is connected. Oops, let's put our ethyl group on here as well. And now you'll see we've got a di-substituted compound. Alright, so now we've got an ethyl group here and a propyl group here, and they're both connected to the center carbon of what was the acetoacetic ester. Alright, so we've gotten up to this step here. Then what we can do is we can hydrolyze the ester, and we hydrolyze the ester by adding H2O and H+, or if you like, just H3O+. I'll write that down as well. Either one of those would do fine. They both mean the same thing. Alright, so what that will do is it will take the methyl ester and convert it into a carboxylic acid. If you want more information about how that happens, then you can go ahead and look at the test 3 on hydrolysis of esters. So yeah, we'd also end up with methanol as a product of that step as well. Then what happens is we can take this and we can heat it, and when we heat it, it decarboxylates. That is, we lose this whole group here and we end up with CO2 as a product as well as our methyl ketone. Now I want to show you how that occurs. In order to do that, I'm going to have to draw the carboxylic acid just a little bit differently to how I've drawn it above here. Okay, we've got the ethyl group, we've got the propyl group. Now all I've done here is I've rotated this bond and put the OH up here and put the C double bond O down here. So I've just rotated this, rotated that bond. Now when I do that, I can then see this undergo a electrocyclic type process, and you can see how this works. Very much like a Diels-Alder reaction if you look at it. And you can see what we end up with here is this. The double bond formed here. And that's how we get our CO2 as a product. But you'll notice this is a special situation. This is an enol, and we know that enols are in equilibrium with their ketone counterparts. So this arrow here is coming from the OH bond and going to the space between the C and the H, and that's how we're going to end up with our other product, which is the methyl ketone. Alright, so that explains what we're doing with the acetoacetic ester synthesis, the AAE synthesis. What I'm going to do now is something a little bit tricky. I'm going to go ahead and convert this acetoacetic ester synthesis into a malonic ester synthesis. That's very easily done. All I do is I change this to an OME, which makes that an OME, and that an OME, and this will turn into an OH. So that's the other wrinkle that's different from the acetoacetic ester synthesis, is that because we got the two ester groups, when we do the hydrolysis, both of those ester groups get hydrolyzed to give a carboxylic acid. And instead of a methyl ketone as a product, we get a carboxylic acid as a product. And just showing you that last step again on the decarboxylation. Whoops. Instead of a methyl ketone that we had earlier, we now have a carboxylic acid group here. But you see that the process is going to be pretty much the same if we look at the mechanism for forming the resultant carboxylic acid. Alright, so again, you'll see the arrows. And what we end up with is the enol from a carboxylic acid. And we end up with the CO2 here. And again, let me draw that out a little bit better. Draw this out with the OH bond, and you can see that we can again form the carboxylic acid, which is our product. So you can see that the differences between the acetoacetic ester and the malonic ester, they're not really that great. The only real difference being that because we start off with an OMe here, we end up with an OH rather than a methyl group as we do in the case of the acetoacetic ester.